Our next notion is that of one-sided limits. One-sided limits. Forgot my hyphen. One-sided limits. Consider the square root function. Now, we all know the square root function from our glory days back in basic algebra. The question is, what is the limit as x goes to 0 of the square root function? As x gets closer and closer and closer to 0 on the x-axis, the question is, what is happening on the y-axis? Well, you might think, well, as you get closer and closer to 0, the y values are also getting closer and closer to 0. That might seem to be pretty straightforward. However, the key is, if we make a delta interval around 0, we need to be free to approach this from either direction. And if I approach from only values bigger than 0, then there's no problem. If I use a value less than 0, then this function is not defined. If I take x equal to something very close to 0, 0.0001 negative, that function value does not exist. And so this, and there are other problems of a similar ilk, we may have some issues if we're allowing x to go to 0 without regard to whether we're coming through values bigger than 0 or values less than 0. More generally, there's nothing magic about 0. We're approaching a value c, or a, we're approaching a, and we can approach a through values greater than a or values less than a. We can approach from the right or we can approach from the left. When we write this, what we're saying is anything goes. It's unrestricted. You can go right and then left and then right and then left and then left, left and then right and left and right, right. It doesn't matter which ones you pick. If we're just allowing this, here's 0. Here's my delta interval. If we're just allowing this to happen, then you can be here. So long as you're getting close to 0, you can hop over whenever you want to. As long as you're getting closer to 0. We want to take a look at restricting that so that we only approach from one direction or the other. And that's what we're talking about here. That's this notion of one-sided limits. What I have written here is called the unrestricted. This is unrestricted because there is no restriction. But we now consider the limit as x approaches 0 of the square root of x. And what we do is we put a little plus sign as if it were an exponent. It's not. It's just a little signifier. This is like an indicator. The limit as x goes to 0, a little plus. And the way you read this is the limit as x approaches 0, or x gets close to 0, from the right. You only approach 0 through values greater than 0. The limit from the right, or the right-hand limit, sometimes we'll say. The one-sided limit, you're only approaching 0 from the right. For our problem, that makes things a lot easier. If you're approaching 0 from the right on the x-axis, that means you're approaching 0 on the y-axis, and there's no problem. Substitute, simplify, you're out. The same techniques apply as before. Substitute, simplify. If that gives you a result, that's wonderful. If it doesn't, do some algebra, simplify, try. The same kind of principles apply. There are a few dicey problems where we'll have to learn how to handle those, but generally it's the same procedure. But then we could also have the limit, x approaches 0, and you put the negative sign as if it were a little exponent. And that would be what happens if you're approaching through values less than 0. You're approaching from the left, smaller than. This is the one-sided approach from the left. Well, in this case, this does not exist because the function is not defined for those values. These values are not in the domain of the function. So we can have one-sided limits. Now, we'll take a look at these in more detail later on. But here's one place that particularly comes into play. Continuous on a closed interval. Now this is a little subtle. Here's A, here's B. We've talked about continuous on the open interval. A function is continuous on the open interval if it's continuous at each point in the interval. Remember, for the open interval, neither A nor B is in the interval for the open interval. The open interval does not contain the endpoints. Now we do contain the endpoints, but we do not contain anything that lies beyond the endpoints. So we might be talking about that curve, including the endpoints. And so what do we mean by continuity at an endpoint? Continuity at an endpoint. At the left endpoint. Look, this is very tricky for some students. If it's the left endpoint, that means the function's in here. The left endpoint you can only approach from the right. And the right endpoint, the function's in here. The right endpoint you can only approach from the left. Here's the left endpoint, you can only approach from the right. Here's the right endpoint, you can only approach from the left. And so, for a generic garden variety point, C, we would need to have, the three conditions for continuity is, we would need to have f of c defined. We would need to have the limit as x approaches c of f of x defined. And then the third requirement, you remember the third requirement is these must equal each other. This has to equal the function value that we found in step 1. The result from step 2 must equal the result from step 2 must equal the result from step 1. So this is if we're talking about C in the interior of the interval. But what if we're talking about at the left endpoint, A? Now we slightly modify this. Number 1, we require f of A to be defined. So far, so good. Number 2, let me write that borderline legibly. That's borderline. Number 2, at A, we want the limit to exist, but remember, for A, we only want the limit from the right-hand direction approach. The limit as x approaches A from the right of f of x is defined. And then step 3 is this answer must equal this answer. So step 3 is the answer you got for step 1. F of A, I was arriving in the correct sequence here. The limit x approaches A from the right must equal the value you got for the start. So the answer you got for number 2 must equal the answer you got for number 1. The key is this. For a point in the interior, it's the unrestricted limit. For the left endpoint, you must approach only from the right. And then as it clears, similarly, we're going to have a similar set of rules for the left endpoint. For the right endpoint. For the right endpoint, you must approach only from the left. And so we can say we can make at a right endpoint B, f of B must be defined, but the limit as you approach B from the left must be defined, and those answers must equal each other. All right? That's the requirement, the technical requirements for continuity on a closed interval. For our purposes, this is the good news from your side of the camera. For our purposes, the overwhelming majority of things we're going to be doing, you will just be given that. You are given continuity on the closed interval. For the overwhelming majority of what we're doing, continuity on a closed interval. Remember, continuity means no holes, no jumps, no vertical asymptotes. And so if you're given continuity on the entire closed interval, That means nowhere in the interior and nowhere on the ends. You have no holes, no jumps, no vertical asymptotes. You don't have a vertical asymptote at either end. You don't have a hole at either end. You don't have a jump at either end. Anywhere in the middle. So when we say continuous on a closed interval, no holes, no jumps, no vertical asymptotes. And we'll end with this. This is a user-friendly version. Here's a user-friendly way to think of it. Continuous on a closed interval, here is a way to think of it. You can draw the picture without lifting. You can draw the picture without lifting, and in my case, I can draw this without lifting the chalk. Continuous means I draw without lifting the chalk. So that means there are no vertical asymptotes, because if there were a vertical asymptote, I would need to lift to cross over and then come back down. Right? So if you can draw without lifting, that means there's no vertical asymptote. If you can draw without lifting, that means there are no jumps. If you can draw without lifting, that means this never happens. Yeah? If you can draw without lifting, this never happens. If you can draw without lifting, there are no holes. Right? Now remember, I had a student one time said, yeah, you can draw that, because look what the student did. The student said, you can do this, and then you can go around the hole, and then you can come back around and keep going, and that's not what we're talking about. What we mean when we draw this is there is a gap of infinitely small size, and we only draw the circle to help reduce the possibility of confusion. So when we say a function is continuous on the closed interval, no holes, no jumps, no vertical asymptotes. Continuity means no holes, no jumps, no vertical asymptotes. We'll look at a few other pieces in a little bit more detail, but no holes, no jumps, no vertical asymptotes.